All right, we have a request. This is 6.2, number 5. So we have vector y, we have vector u. It says compute the distance from y to the line through u and the origin. So the line that goes through u and the origin is the span of the vector u. We want to know the distance from y to that line. So we're going to find the projection of y onto that line. We're going to find that orthogonal vector z, and then we're going to find the length of z, and the length of z will be how far that vector is to the line. So here's a picture. So this is in R2. We've got some line going through the origin. We have vector y, and we want to project y onto the line, so that'll give us y hat, right? And then we want the vector that's orthogonal, such that when we add y hat to z, we get y, and this guy will have the same distance as this distance here. Right? So we just find the magnitude of this vector, and we'll have how far y is to the line. Okay? So projection, y hat. So we want to dot u with y, dot u with itself, and we multiply that fraction times u, and that'll project y onto u. So y dot u, it's like 48 and 72. Is that 120? I may be wrong. That may be 130. (48) plus 72. 120. I was right. 120. And then u dotted with itself, so it's going to be 36 plus 48. 84. Does that reduce? I'm going to cheat here. You guys don't do this at home, okay? So it's 10 over 7. But you could figure that out pretty easy without the calculator. So this is 60 over 7. This is 80 over 7. So that's y hat. So now we need z. So z is y minus y hat. So y is 8, 9 minus the projection so this would be 56 over 7. This would be 63 over 7. Is that correct? Yeah.
I could be messing something, but
Did I mess up?
U dot U
100? Oh, you're right. $36 plus 64. I did 48. Okay, sorry about that. That's going to make it easier. You guys have to tell me before I do all this work.
Well, you were on the roll, and I didn't want to interrupt you.
Yeah, but I mean that's why you have to interrupt, because I will just keep rolling.
So you know how we feel when you're on the homework? Realize for us to sell out or something?
Okay. Let's check y dot u. So that is 8 times 6 plus 9 times 8. 120. Okay. All right, so it's 12 over 10, which is 6 over 5, right? That's close to 10 over 7. Right? That's right. Is that correct? Okay. So again, z is y minus y hat. So now I'm questioning everything. Y is 8, 9, that's right. Minus so that's 40 over 5. This is 45 over 5. Is that correct? And the last thing is to find the magnitude of z. So we take the sum of the square root of components and find the square root of that. Right, so square root of the sum of the square root of components. So this is 16 over 25. This is 9 over 25. So I get 1. Does that help, Matthew?
Yeah, tell you what, I forgot. I was
Okay. All right. That one's, a little bit involved. You got to go through several things to get there. Does anybody else have a homework question? I sent it off. I don't. They haven't. They haven't told me if they fixed it. It usually takes about a week, so we'll see. Yeah. Yeah. Yeah, we finished that last week on Friday.
What problem was that again on 6.3 that was messed up?
It was the third one. Yeah, like I was able to do it. Kelly had enough time.
If you think you got that one wrong, you can send that to me and I'll fix it. I could fix the grade. All right. I want to do case study.
Did you happen to cover it in case study on Friday class?
I did. I covered what's called the Graham-Schmidt process. It's the last 2 or 3 questions on the case study.
Okay. And you said that you will upload that video?
I uploaded it right before class.
Oh, okay.
Yeah, so it's up there now. So I did like the last 2 pages on the 6.3 notes, and I did a couple of examples of the Graham-Schmidt process. So this is number 1 on the case study, and it says let the matrix below act on C2. So what do you think C2 is? So C with the double line is all complex numbers. You know, just a reminder, complex numbers are numbers where the form a plus bi, where I is the complex, or I is the imaginary number square root of -1. So a and b would be real, but b times I would be imaginary, but b is a real coefficient. And a plus bi would be complex. Now notice that if b is 0, then you just have a real number. So that means the real numbers are part of the complex numbers. So real numbers are also complex. So complex numbers are a bigger set. And if a is 0, then we say it's pure imaginary. So pure imaginary numbers are also complex. So you get this complex set. The real numbers are part of it. The imaginary numbers are part of it. But the complex set is bigger, and it encompasses both of those. So in the middle, you have all these sums of the two. Right? So we have a matrix here, and we want to find the eigenvalues. And then we'll find a basis for each eigenspace in C2. So C2 would be all 2-dimensional vectors where the entries can be complex numbers. So up until now, we've only had real number entries. So now we're going to allow complex numbers to be entries in our vectors. So we do this the same way. we need determinant of A minus lambda I. We subtract lambda from the main diagonal. So multiply that diagonal, multiply the other diagonal, times -1. Whoops. Let's see, 3. So I get this one. So that's the characteristic polynomial. So does that thing factor? Does it factor nicely? They all factor, but does it factor nicely? Can you multiply two numbers to get +5 and you add them to get -4? So 5 is prime, right? So the only two options are 5 times 1 and -5 times -1. That's the only way to multiply two nice numbers, right? Two whole numbers and get +5. Do either one of those add up to be -4? No, so it doesn't factor nicely. Okay. In fact, it factors with complex numbers, so that's not very nice. Okay. So we'll solve it using our tried and true method. Complete the square. I'm going to add b over 2 squared to both sides. So b is -4. What's b over 2? -2. We square that, we get 4. Going to add 4 to both sides. Just add 4 to both sides. Now this is a perfect square. Square root of both sides. So I take the square root of -1. What do I get? I. So there's your complex part. Add 2. We get 2 plus or minus I. So we get two different eigenvalues. One is 2 plus I, the other is 2 minus I. So they're complex. Let's see what MyLabs thinks. They say good job. So now we want to find a basis for the eigenspace for the eigenvalue A plus BI. So you notice that the eigenvalues that are complex come in conjugate pairs, right? So we call this a conjugate pair. So one eigenvalue is the complex conjugate of the other. You guys remember what conjugate means, right? If you don't know, ask. Okay, it's okay to ask if you don't know. So they always come in conjugate pairs. So now we need to find basis for the eigenspace, and it says the first one's going to be A plus BI. So let's use 2 plus I. So we're going to find eigenvectors for this eigenvalue, lambda equals 2 plus I. We need to solve this equation. A minus lambda I, and this is the different I, this is identity I, times x equals 0. Right, this is lambda. A minus lambda I times x equals 0, right? We solved that equation. So what that means is we take A and subtract 2 minus I from the main diagonal. And then we augment it with 0, right, and solve. So A, 1, 1, negative 2, 3. So 1 minus lambda, 3 minus lambda. And let me go ahead and augment. Right. Just subtracting lambda from the main diagonal. So 1 minus lambda. So if we take 1 and subtract 2 minus I, what do you get? Negative 1 minus I. Good. 1 minus 2 is negative 1, and then you also have to subtract the I. You can't combine those, so you just leave it. And then we have 3 minus lambda, so 3 minus 2 would be positive 1, and then minus I. So now we have to row reduce this. And your calculator won't do it.
Even if you set it to complex mode?
I'm sorry?
Even if you set it to complex mode?
It should not. It should not. TI-89 will do it, and the Inspire CAS will do it, but your 84 shouldn't. But it's not difficult to do. Okay? So,
Divide by negative 1 minus I.
well, how do you divide complex numbers? So there's a way to do it with the trig form of a complex number. You could do that. But we really don't care if we make it 1 right now. So really, if we could just make this a real number, right? We'll just make this a real number, then we can use this 1 to make it 0. Or if it was just a real number, we would divide by that real number. Okay, so a way to make this a real number is to multiply by the conjugate. Right? If you multiply a complex number by its conjugate, you get a real number. So let's multiply this row by negative 1 plus I. Okay? So this is row 1 replaced with negative 1 plus I, row 1. And when you multiply a complex number times another complex number, it's like multiplying 2 binomials. You just fold it out, right? Just like we did a minute ago. We fold the two binomials out. So negative 1 times negative 1 is positive 1, and then negative I and plus I. And you want those to cancel out. And that's the point. We want to get rid of the complex part, the imaginary part. And then the last one is negative I times I. So it'll be negative I squared. So what is I squared? Negative 1. So negative 1 times negative 1 be positive 1. So this is positive 1. Okay, then we have negative 2 times negative 1 plus I. I don't care about multiplying that out yet. So this is 1 plus 1. Here, if I factor out a negative 1, I can make this 2 times 1 minus I, like that. You guys agree with that? Do you see that this first row is a multiple of the second? So that tells you that the eigenvalue is correct, right? The eigenvalue is the one that makes your determinant equal to 0, and that happens if one row is a multiple of the other. So I could multiply the second row by negative 2 and add it to the first row. I get a row of zeros. And then I could swap the 2 rows, and it's going to reduce to this.
So the free variable can be complex.
I'm sorry?
So the free variable can have a complex number.
Yes. So when we have a free variable here, we can make it real, we can make it complex. As long as we don't create a 0 vector for our eigenvector, doesn't matter. So say here x1 is negative 1 plus I, or 1 minus I times x2, and x2 is free. So let's look at the answer choices, because we can choose anything for x2, right? But we need to choose the one that the book chose for its answer. Does that make sense? Because unfortunately this one is multiple choice, which kind of stinks. So we have a bunch of choices here. So it looks like A works. Do you see A? If we let x2 be 1, then this becomes negative 1 plus I when we multiply that negative 1 inside. So I think A is correct. There are infinitely many choices. You could let x2 be I, and it'll make both terms imaginary. You could make x2 be the conjugate of that, and it would make the first entry real and the second entry complex. There's a lot of different ways to show this. It's not going to be as easy to see them, okay? But this one works. Okay, so now we have to do it for the second one. So for lambda equals 2 minus I, the second eigenvalue, solve A minus lambda I x equals 0. And lambda is 2 minus I. So the main diagonal of A was 1 and 3, right? So we have to subtract lambda from 1 and 3. So 1 minus 2 is still that negative 1, except now we have plus I because we have a negative I, right? 2 negatives on the I. And then 3 minus 2 is 1, and again plus I here. You could, before we multiplied this by the conjugate, right? And made that one real, and then we added. We could multiply this row by 1 minus I and add it to this row, and it'll make that 0. We could do it that way. Do you want to try that way?
Sure.
Okay. So now we're going to say row 1 is row 1 plus 1 minus I times row 2. If this 1 is 1 minus I, then when we add it to here, we get 0. So row 2 doesn't change. So when I multiply row 2 by 1 minus I and add it to row 1, all that will cancel out and leave me with 0. Do you agree? So now we got to multiply 1 plus I times 1 minus I and add it to negative 2. So I'm just going to do this to the side. Those are conjugates, right? So 1 plus I minus I squared. Those cancel. Negative I squared is positive 1. 1 plus 1 is positive 2. So when I add 2 to negative 2, I get 0. So now we just need to swap the two rows. And we get x1 equals negative 1 plus I x2, and x2 is free. So let's do the same thing. Let's make that 1. So what will this be? That'll be 1, and then we multiply the negative, so it'll be negative 1 minus I. And that looks like D. Okay. Let's look at these two. So our first eigenvector was -1 plus I, 1. And our second eigenvector was -1 minus I, 1. So what do you think? They're also conjugates. So your eigenvalues always come in conjugate pairs, and their eigenvectors will be conjugate pairs, which means actually we didn't have to do all this for the second eigenvector. Right? So once we knew the first eigenvector was -1 plus I1, we could have created our second eigenvector automatically, just with the conjugate. And it always works. It always happens that way. If your eigenvalues are complex, they always happen in conjugate pairs. And the eigenvectors that go with those two eigenvalues will be conjugate pairs. So you actually only have to do this stuff one time, unless you've got 4 complex eigenvalues. But for just the pair, you only have to do this work one time to get the eigenvector and then take the conjugate of it, the complex conjugate of it, to get the second eigenvector. So all you have to do is switch, for the second eigenvector, switch the sign of the complex or the imaginary part of the complex numbers, wherever they are in the vectors, okay? If you have complex numbers in both terms, you still complex conjugate both of them. You just change the sign of the imaginary part. Okay? Are we good with that? So it's a little bit more difficult, but you also get a shortcut built into it. So it's not that much worse than what we did before. You will not get a 3x3 complex conjugate or complex eigenvalue problem, but that one's a little bit more difficult, so it's not too bad. But just know once you get that second conjugate, or once you get that eigenvalue pair and you get that first eigenvector, you can get the second one pretty easy. Okay. Any questions? This is number 3 on the case study. Number 3 on the case study. So just a review. Oops. This is called a difference equation, where it's a recursive matrix transformation where you multiply the matrix A times the previous vector to get the next vector. Okay? We did this with population models and other things. Okay? And we said That's the same as multiplying A k times the original vector x sub 0, your initial vector. Well, actually one more. It's actually one more. So we usually change it to this. So if A is diagonalizable, if A is square and it has, say, n columns, if it has n linearly independent eigenvectors, then you can rewrite this equation as this. Depending on how many eigenvalues and eigenvectors you have. So lambdas are the eigenvalues and the v's are the eigenvectors. Okay. We covered this a long time ago, so I know that may not be fresh, but we covered it at the end of 5.2 maybe. We did an example. So our problem tells us that A is 2 by 2, and it has two different eigenvalues, 2 and 1/2. The eigenvectors that correspond to those eigenvalues are V1 and V2. And we have this difference equation with our initial vector is 9, 1. X sub 0 is 9, 1. So it says compute x1 equals A times x sub 0. So A is not known. It just tells us it's 2 by 2. We know its eigenvalues and we know the eigenvectors, but we don't know A. And we do not need to know A. Okay? So are these two independent? They are. You also know they're independent because they're eigenvectors for the same matrix. Okay? For different eigenvalues. I have two R2 vectors, right, that are independent. What does that mean? I have two independent R2 vectors. That means those two vectors span R2, right? Okay? That means this guy is also in R2. It means I can rewrite this vector as a linear combination of those two. So that's your first step. You need to solve this equation for the constants, C1 and C2. So you can do that like we've always done it. Put the vectors in a matrix. We're going to augment with x sub 0. We're looking for C1 and C2. Those are our variables. So let's cheat. This is 2 by 3. So we get 5 and negative 4 as our solution. 5 and negative 4. So C1 is 5 and C2 is negative 4. Okay, so we want to compute x1. It's a times x of 0. Well, x of 0 is 5v1 minus 4v2. So I'm just going to replace it. If you have questions, ask. Everybody with me? Okay. I'm getting some bad looks. So can multiply a inside, and we can factor out these constants. So we get this. So this guy right here is A times an eigenvector. And the whole property of eigenvalues and eigenvectors that we like is A times an eigenvector is the same as the eigenvalue times the eigenvector. So that's why we don't need to know what A is. And that's why we want to change x of 0 into eigenvectors. Right? So now this is 5 times the eigenvalue for v1. Remember the eigenvalue? It's 2. And then v1 is 1, 1. So this is 5 times 2 times 1, 1. And this is 4 times 1/2 times negative 1, 1. So we have second eigenvalue 1/2, second eigenvector is negative 1, 1. And we can compute all this. So this is 10. This is 2, negative 2, right? So it looks like 12 and 8. Without knowing what A is, right, we were able to do this. We're trying to eliminate A anyway because it's going to be less operations for a computer to compute all these matrix multiplications by just using these eigenvalues and eigenvectors. But the only thing is you have to have enough eigenvectors. So we needed 2 of them at least, right, to be able to do this. Okay. Guess we need to check our answer, make sure that we didn't mess up. That was nice work. All right, so now we need a formula for x of k. So just generically, what would we do if we multiplied, or if we wanted the kth term of this sequence, the kth vector? So for v1, we need to multiply 5 times 2 to the kth power, right? So if we keep multiplying a times that, if we keep multiplying a times this, then we keep multiplying a times this guy, we keep multiplying by 2. So the 2 gets multiplied k times. And here the 1/2 gets multiplied k times. So instead of multiplying a k times, we multiply the lambdas. So this is going to be minus 4 1/2 to the k. What would happen as k goes to infinity? What happens to the first term? It's going to go to infinity, right, for both entries of our vector, right? Both vector entries would go to infinity. What about this side? That would go to 0, right? So it would end up being just a multiple of this vector here, but the multiple will just keep growing to infinity. Okay? You guys want to do another one of those? So that one's got more vectors. So let's skip that one. So let's look at this guy. This is number 5. It says, denote owl and wood rat populations in a particular area at time k by this x of k. So k is in months. L sub k is the number of owls in the area. I don't know why they used L, but I guess it's for owl. And R sub k is the number in thousands of wood rats. So R is in thousands, and L is in single digit, just number of owls. And we know that L sub k plus 1 is 0.2 times L sub k plus 0.2 R sub k. And R sub k plus 1 is negative 0.2 L sub k plus 0.7 R sub k. The owl population and the rat population are dependent on each other because the owls need the rats to eat. But if they eat too many, then there won't be rats, so there'll be less owls, right? if there are a lot more rats, then there will be more owls, and when there are more owls, then there will be less rats. So they're kind of interconnected that way. Does that make sense? So this is why we have the owl population depends on the rat population, and the rat population also depends on the owl population. Okay. All right, so determine the evolution of this system. Give a formula for x of k. Does the owl population grow or decline? So let me screenshot this. So what this says is that x of k plus 1 would be L sub k plus 1, R sub k plus 1. And we know L sub k plus 1 is 0.2 L sub k plus 0.2 R sub k. And R sub k plus 1 is negative 0.2 L sub k plus 0.7 R sub k. And that is the same. You should be able to see this, right? It's 0.2x plus 0.2y equals negative 0.2x plus 0.7y, right? This is this matrix times this vector. So we have a difference equation, right? It's x of k plus 1 equals a times x of k. That's x of k. Right. So we want to find a formula. We do not have an initial vector x of 0. So we don't have to worry about writing x of 0 as a linear combination of eigenvectors. But we're going to do it without knowing the constants. Okay. So I need the eigenvalues of A. When you find eigenvalues, you don't need to do anything to A first. It's tempting to multiply these by 10, right? And then find the eigenvalues. Don't do it. You have to just leave it alone and just find the eigenvalues just the way it is, okay? So determinant of 0.2 minus lambda, negative 0.2, positive 0.2, 0.7 minus lambda. Yeah, it's tempting to try to fix A so this part will be easier, but you can't do it. You know, you could do it here, but you have to multiply the lambdas by 10 as well, and then you have to know that your determinant is a factor of 10, right? You have to get that factor of 10. And if you do it to both rows, then you're multiplying by 100. So I just think it's better just to leave it the way it is, not try to be cute. I mean, I like being cute, but if I can make something easy by being cute, then I'll do it. But this one, it's not worth it. You can't put lipstick on this pig. Okay. All right, so this is 0.14 minus 0.2 lambda minus 0.7 lambda plus lambda squared plus 0.04. So can we multiply two numbers to get positive 0.2 and add them to get negative 0.9? Yeah. Yes, you're right. Man. Thank you. Well, I know that one will work. Maybe. Yeah, that one works. So how does it factor? Yes. Negative 0.6 and negative 0.3. So lambda 1 is 0.6. Lambda 2 is 0.3. So now we need eigenvectors. So we'll need to solve a minus 0.6i x equals 0. Let's see, so A is over there. So this is 0.2, this is negative 0.2, that will change. The main diagonal changes. So this is 0.2 minus 0.6, negative 0.4. And this is 0.7 minus 0.6, we get 0.1. Is one row a multiple of the other? Yeah. So if I multiply the second row by negative 2 and add it to the first, I'll get a row of zeros. I'll put that row of zeros at the bottom. this guy, let's multiply by -10. We get that. And then we divide by 2. So x1 is 1/2 x2. x2 is free. Let's let it be 2. So we get this eigenvector 1, 2, like that. Now we need to do this again for the second eigenvalue. What was the second one? 0.3? So I subtract 0.3 from the main diagonal. Are the two rows multiples? Yep. So if we multiply the first row by -2 and add to the second, we get a row of zeros. Multiply the first row by -10. We get that. So we get x1 is 2x2. x2 is free, so we get another eigenvector 2, 1 instead of 1, 2. So now, x of k, instead of a to the k x sub 0, we're going to say this is the same as c1.6 to the k times our first eigenvector, 1, 2, plus c2 0.3 to the k times 2, 1. If we had this initial vector x sub 0, we could figure out what c1 and c2 are. Okay, we would figure out what linear combination of the eigenvectors would give us x sub 0, but we don't have x sub 0 here. So let's see what matches up here. It's like the last one, D. We in agreement? Yep. That was it. So what happens as k goes to infinity? they're both going to go to 0, right? So they're both going to be in decline here. So eventually both of them will die out at this, if they continue on this path.